to the class of 2023 High Star presentations. So High Star, as most of you probably know, is a program for middle school and high school students that we're trying to teach them how to do real research. And part of real research is disseminating that research, and this is part of that, sharing what they found this week with you. Our first group is the asteroid group's composition of a space potato. So the composition of Didymos. And I will introduce them to you. First is Jet Orion Teagarden. Orion is a returning High Star student. You've been here, what, 3, 4, 5 times? Yeah. So n times at this point. James Anchetta is also a returning student. This is your second year, correct? All right. CJ Paquet, did I pronounce that right?
It's actually Pakai.
Pakai. CJ Pakai, my apologies, is a first-time student, and Asher Tokuoka. Close? Okay. Correct? No. Okay. Tokuoka. Did I get it there? Okay, say it.
Tokuoka.
Tokuoka. Okay. All right, so I will turn the time over to you guys.
Okay, so our project was on the composition of a space potato named Didymos. The reason why we say space potato is because asteroids look like a space potato. Yeah.
The DART mission launched in November 23rd, 2021. This was done to see if we are able to redirect the path of an asteroid named Didymos. Didymos is an asteroid system where a smaller asteroid, Dimorphos, orbits around the bigger Didymos. On September 26, 2022, DART smashed into Didymos, shortening the orbit by 32 minutes.
Our main goal of this project is to find the composition of the asteroid Didymos. By comparing the color and Tholen spectral type of known reference asteroids to Didymos' color, we can see the Tholen type of Didymos giving us its composition. To take measurements of the targets, we must do a process called photometry, which takes the difference between the target brightness and the sky in the background to measure the actual brightness of the target. A solar analog is a star with a constant brightness that is typically used to account for different telescope sensitivities across different images. We used a Muscat instrument that took photos in different color bands simultaneously, that being green, red, infrared, and Z, which is a deeper infrared.
Tholen spectral types are a way to classify asteroids based on their composition. The composition is based on the color of the asteroid, but not the color of the light reflected off of it. This means we must find the true color of Didymos in order to classify it properly, as the sunlight would simply be white. So there are C-type asteroids. They are made out of carbonates. S-type asteroids, which are made out of silicon, and X-type asteroids, which are made out of metals.
Alright, so for our method, we first obtained all of our data from the Las Cumbres Observatory Global Telescope Network. Then we began by, we first needed to measure the color of the asteroid, but we don't want to measure the color that's being reflected from the light of the asteroid, because that's the sunlight being reflected, and that would just be white light. So, to start figuring out what the color of the actual asteroid is we first took the average flux of a solar analog, which is a star with a constant brightness, and the average flux of our target Didymos. And so what flux is it's a measurement, it's a unit of brightness that is pretty much based on the amount of light let into the telescope image, or into one image from the telescope. So we took our target flux, our average target flux, and divided it by the average flux of the solar analog. And then that gives us something called the relative spectral albedo. So what the relative spectral albedo is it tells us how much light is absorbed versus reflected off of the asteroid. So, but you might have noticed that it's relative. And so what it's actually relative to is the amount of brightness from the asteroid, but the amount of brightness differs depending on the distance and the size of the asteroid. And we don't know the distance or the size of the asteroid. So how we figure out the actual color, or how we make the spectral albedo relative to the color rather than the brightness, is we get a baseline. And so how we get a baseline is we divide each spectral albedo value for each color filter, and we divide it by just one color filter. And so for example, what we did is we chose red. And so dividing red by red, no matter the value of the spectral albedo of red, just equals 1, and that's our baseline. Then if G divided by R equals 0.5, then there would be half as much green light as there is red light. And yeah. And so for our results, after graphing the colors relative to the red band, we've concluded that Didymos is an S-type asteroid. And so this means that Didymos is mostly made out of silicon and rock. And so if you look on this graph here, you can see that the blue dots are C-types, the red dots are S-types, and the green dot is our target, and the yellow dot is X-types. And so you can see there's some overlap between X-types and C-types. And the X-axis is green light, so further along the X-axis is more green light, further along the Y-axis is more infrared, and then this is infrared by infrared, deeper infrared on the Y-axis on that graph. And so you can see that there's a bit of overlap with C and X-types, and then there's a lot less green light for S-types. And then that green dot right here falls right in the S-types, meaning there's a lot less green light of our target, and there's it's most likely an S-type. And then to this graph over here, you can see that it falls again within the S-types, as it has the most infrared light. S-types have the most infrared light by far, and this has a lot of infrared light.
We also created a light curve of Didymos, which is a graph of brightness over time, brightness being the y-axis and time being the x-axis. We use Julian date for the time, which is just a measurement of days. The light curve shows, so an asteroid is usually oblong, and the light curve shows how much light we are getting from the asteroid. And when we see the longer side of the asteroid, there's more light, so there's a bigger dip. And when there's a smaller dip, we're seeing the smaller side and there's less light. This graph is a bit longer than one period being one rotation. It shows 2.4 hours, and the period is about 2.3 hours for one rotation of Didymos. If we were to multiply the 2.4 hours by 10, there would be 10 rotations per 24 hours, and that's fast enough to spin apart, for the object to spin apart. And if we were to multiply Didymos's spin rate, then by 10, it would be 10 rotations in 23 hours, and that's barely fast enough to spin apart, which still means spinning apart. Yeah. And then this is Didymos after impact, and it has comet-like activity.
We've concluded that Didymos is an S-type asteroid, and it is made of rocks and silicon. Studying the composition and physical properties, as well as the motion and behavior of asteroids, is important for helping us understand more about the solar system and the objects within them.
Any questions?
All right. All right, well, let's thank them. So no, are there any questions? Yes, Carol.
So how do you make sure you're getting just the color of Didymos and not dimorphous?
How do you know you're getting just the color of Didymos and not Dimorphos?
That's a good question. So we kind of don't, but how we actually do know that is if we see a transit in the data or not. And so as far as we know, there's no transit in the data, which means we're not seeing Dimorphos, but it's possible, if I go back to the slide, it's possible the beginning of this light curve, it's possible this could be a transit because for a moon it would be a kind of short transit. But we're pretty sure that it's not a transit because it seems to repeat over here at the end of it. So we're pretty sure we're just looking at, what's it called? Just the target, not the moon.
Alright. Alright, any other questions? That's great. Yes?
I was just curious, you stated that, I guess the first one rotated 10 times in 24 hours and it was spinning fast enough to pull apart, correct? And then the next one you said it was spinning 10 times in 23 hours and it might have enough or it was barely enough to start pulling apart the asteroid. I don't understand that. I would think if it spun 10 times in a less period of time, it's actually spinning faster.
Yeah, if it spins 10 times.
Repeat the question, please, also.
Repeat.
Yes. Repeat the questions.
Oh yeah. So so you're asking if having the same like 10 rotations per day in less than a day means it's spinning fast enough to spin apart?
Well, I was confused because if 10 times in 24 hours was definitely faster, and then the folks stated that in 23 hours it's spun 10 times and it might be fast enough or it's barely fast enough to pull apart. I would assume that if it's spun 10 times in 23 hours, it's actually spinning faster than the one that's spinning 10
Or yeah. So what we meant by that is just if it needs to spin 10 times per day or faster
it doesn't matter.
to be able to spin apart, as long as it's at 10 times per day. We were just saying that because that's like the minimum speed it needs, and so it's just barely above that minimum speed it needs to spin apart. Yeah.
So as long as you're rotating more than 10 times a day.
Yeah, and then also you might think that the gravity would play a part into that, but when you calculate the angular momentum based off the gravity of it, it actually, the radius cancels out. There's a lot of math for that we didn't really go into, but the radius cancels out and the gravity actually doesn't matter about that. So,
Any other questions?
yeah.
How big is Didymos?
So we actually we did not take measurements of the size of Didymos. We're actually not sure. Yeah. Okay. Any more questions? All right. Well, thank you.
This is our star group. So as we go a little further from the solar system, first step is I would imagine stars. And so Ginger Hill is a first-time attendee of High Star, and Reina Lana. Reina Lana. Did I get it right? Reina Melana. Okay, Reina Melana. My apologies, I had it written down wrong. Is also a first-time attendee of High Star, and they had a very interesting result that I think they're going to tell you about. Didn't you? Yes? Something very exciting. All right, I'll turn it over to you two. Okay, take it away.
Hello, this is our presentation on identifying binary stars. Our mentor is Rena Lee, and the people who did this research are Ginger and Reina.
Overall, our main focus or question for this project was if we are looking at a single or a binary star.
Now, what is a binary star? Well, a binary star is a set of two stars gravitationally bound together. They are both orbiting a common center of mass, So imagine twin stars on similar orbits together. An estimated half of stars in the sky are actually binary. Here's an artist's rendition of a binary star. They're interacting and causing a lot of interesting evolutionary processes for each other.
Next up, why do we even care about binary stars? We study binary stars to more accurately classify them. This helps us to find truly how many stars are in the sky. So it helps us to know the true population of stars in the sky. It also helps us to know the characteristics of each individual star. For instance, this can help us to know their true size, brightness, age, and distance, to know more about the star. For instance, if we know that we are seeing 2 stars rather than 1, then we know that both of them added together equal the amount of brightness that we are seeing rather than just 1 star. It helps us to know the true characteristics as well as the true population of stars in the sky. This image here is also another artist's rendition, so it is not a real photo of binary stars.
So how do we find binary stars? Well, one way we can identify binary stars is by looking at a graph called a light curve, which measures a star's overall brightness over time. If 2 stars are orbiting together, when the larger one is blocked out by the smaller one, there will be a large amount of overall brightness blocked out. Then, when the smaller one is blocked out, there will be only a small amount of brightness decrease. If this is a binary star per se, there will be a periodic dip in the light curve of when the larger star is eclipsed than the smaller one. This we can find in the light curve graph using photometry.
Next of all is TESS. TESS is a space telescope that stands for Transiting Exoplanet Search Satellite. We used a Python package called LightCurve to search TESS's data for some of the information we used to plot the light curves for our objects.
Now, another way we can identify binary stars is by using astrometry, or the study of how the star moves in the sky. In the figure to the right, it shows a star over time in a circular or elliptical motion. There isn't much else this could be orbiting, so we can conclude that it must be in a gravitational orbit with another star around the center of mass, making it a binary star.
We also use Gaia to help us with astrometry. Gaia is a space telescope that helps us by precisely mapping all of the stars in the sky. It measures these stars' positions over time, so we can keep track of their motion through space. A single star would move roughly in a linear trajectory, as you can see on the screen, through space due to its orbital motion. Due to its orbital motion if it is not interacting with another object. For binary stars, the wobble of the star's motion through space, or that is due to orbital motion, is measured by Gaia's Roux value. Roux stands for renormalized unit weight error, and it basically measures the error of fitting a star's motion to this linear trajectory. Roux values greater than 1.4 give us evidence that the star is a binary, because it's not behaving on that linear trajectory as a single star should.
Okay, so lastly, the last way we can use to find binary stars is by using spectroscopy. By using spectroscopy, we look for 2 sets of spectral lines in a single spectrum. This indicated the presence of 2 stars instead of 1. In the figure, we can see that there are 2 spectral lines. The top line is an example of a single star, and in the bottom line, we can see 2 pairs of the same spectral lines, indicating the presence of a second object.
Another way we can use spectroscopy is by looking for 2 sets of spectral lines on a single spectrum. This indicates the presence of 2 stars instead of 1. In this figure, we can see that there are two spectral lines. The top line is an example of a single star, and on the bottom line, we can see two pairs of the same spectral lines, indicating the presence of a second object because of that double line.
Now for our project, we used spectra that were obtained from NASA Infrared Telescope Facility. The data is in the infrared wavelengths, so wavelengths that are longer than visible light. This is ideal for cooler, fainter targets. In our spectra, since we are looking at cool and faint objects, there are many atomic and molecular species present. Here is a picture of a telescope at Mauna Kea.
Now that we've gotten through some background information, I'll remind you of our main science question. We're looking for our main science question of if we're looking at a single or a binary star. From this, we have formed a hypothesis that if we can find peculiarities in the light curves, astrometric motion, and or the spectra, then we can conclude that this will be a binary star.
Okay, so for our project, we used Python to create plots of spectra. Here we can see that there is a single set of lines, so we can roll out that this source is a double-line spectroscopic binary. We would need data at an additional epoch to know if it is a single-line binary shifting over time. However, there is other evidence that this is a single star. Based on this Roux value of 1.002, the motion through space indicates it is a single star. And on this light curve, there is no variation or the periodic eclipses.
Next off, we have a binary star candidate. We looked through many spectra of different objects, and one interesting object we found was this 2-mass star. Here we have two spectra of a star taken roughly about a year apart, as you can see in the red and black lines. The spectra taken about a year apart were shifted in wavelength. The full spectrum is shown on the left, and we have a zoomed-in version on the right. This is some evidence that the star is a binary because of the shifted wavelengths. However, it still may require some follow-up observations.
We found some other supporting evidence that this is a binary star. The Gaia-Roux value is at 1.8, which means it is showing some orbital motion as it moves through space. We also made a test light curve, which shows some periodic variability.
Alright, so what is going on with this 2-mass object? Based on the short period of time the light curve variations take, the amplitude of variability, and the irregular shapes of these bumps and wiggles from our photometry, astrometry, and spectra, we think that this not only is a binary star, but a rotating ellipsoidal variable binary. This name means that these are two stars that are so close together that they pull on each other with their gravity becoming elongated as they elongate each other.
We mentioned in the project motivation that we study binary stars to better characterize them and understand the true population of stars. Here is a Hertzsprung-Russell diagram, which is the main graph in astronomy used for classifying stars. On the x-axis, we have temperature, and it increases from right to left. On the y-axis, we have luminosity or brightness increasing from bottom to top. It shows stars at different evolutionary phases. Most stars are on what is called the main sequence, in the middle diagonal clump. Binary stars on this type of graph tend to stick out by looking brighter than they should. For our project, we wanted to see if this is the case for the binary candidate we found.
Here we have a variation of the Hertzsprung-Russell diagram from the previous slide called a color magnitude diagram. The color on the x-axis is a proxy for temperature, and the magnitude on the y-axis is a proxy for luminosity. The pink star that you can see marks the two-mass object we found that is binary, while the black star on this diagram shows the single star that we displayed. The rest of the points on this graph are similar stars of this same association as the other two. We can see here that the binary star is on the brighter side of the main sequence. Some additional work we could do is by using the spectroscopic data to determine the masses and brightness of the individual stars that are part of this binary system. Then we could better classify them and the other stars related to them all in this similar group by updating this graph with their true characteristics.
Now here are our acknowledgements. Thank you to everyone who attended our presentation and supported this work. We'll take questions now.
Any questions? Yes. Yes, please do. So repeat the question.
So you're saying if we skipped over the Doppler shift?
Yeah.
Okay. Then I can explain what it is.
Yeah.
Yeah.
Qualitatively.
So let me go back to the slide. Okay. So by using Doppler shift, we can know from what direction the star is moving in our line of sight from the wavelength shifts in the spectral lines. When an object is moving away, it is redshifted, and if it is moving towards us, it is blue shifted. If we see this red and blue shifted pattern, we can tell that a star is in an orbit. Does that kind of answer your question? Yeah.
Yeah, so if we can notice that pattern of the red and blue shift, then we know that it keeps on coming towards us and going away from us in that orbit.
Alright, so any more questions? Yes?
Do you know how long it takes the stars to go around each other?
I'm not sure because we didn't cover that, but I think.
This is likely different on each set of binary stars depending on their size and their system size.
Alright, so any more questions?
Alright, thank you.
Okay, now, thank you very much. Are there any other questions? No? Other questions? All right, well, moving out, hanging around one of these stars that we just heard about might be an exoplanet. And so our next group is our exoplanet group. This is our exoplanet group, and Annika and Chetta is a returning student. You've been to High Star how many times? N times. She's an nth time returner. She's done a lot of work with mostly Galaxies, but wanted to try something a little bit new this time. Holden Suzuki, he's, shall we say, a little bit well known for looking at satellites. He's done quite a bit of satellite work and done some really neat stuff with that, and he's a returning student. He's an N+1 returner if Annika is an N returner. And Dominique Rice is a new student, also wanted to get in on the excitement of exoplanets. So I will turn the time over to them.
Okay, thank you so much. So this is our project, Why Are Some Giant Planets So Giant? So thank you so much to our awesome mentor, Nick Saunders. I'm Holt Suzuki, this is Dominic Rice, and this is Annika Nacheta, and this is our project. So first of all, what is an exoplanet?
An exoplanet is basically any planet that's not in our solar system. Much like our solar system, there are different types of planets. There's two main ones. There's terrestrial planets, which are rockier ones like Earth or Mars, and then there's gas giants, which are big balls of gas, basically, most notably Jupiter. There's also some that are kind of in the middle, like super Earths, and sub-Neptunes, which are just more of a mix.
So, what is a hot Jupiter? This is what our project's sort of focusing on. Hot Jupiters are gas giants, so like Jupiter, that are located close to their stars, making them hot. So hot Jupiters orbit their stars faster, thus they have a greater chance to be picked up on and observed through transits.
Okay, so why is this important? So studying hot Jupiters is really important because, for one, they're basically largely unknown. There's not many of them, and inside of our solar system specifically, we don't have a hot Jupiter. There's no planet like Jupiter in the inner solar system. Another one is that they provide us more information about generally how planetary systems develop. So, for example, if we can understand how a system with a hot Jupiter develops, we can kind of understand more broadly how most of them develop. And then also, because we have a Jupiter in our solar system, we have a gas giant, and it's kind of important for us to understand how gas giants operate.
Okay, so we have exoplanets, we have to discover them, and we do that via transits. Now, what is a transit? An exoplanet transit specifically occurs when an exoplanet passes between a star and an observer, which would be us in this case. How we detect it is it dims the light we're receiving from a star, which we can then measure that light received with a light curve, which was mentioned earlier, and is a graph of brightness over time. Now, exoplanet detection using the transit method, which is what this is called, is biased towards larger planets with short orbits, much like a hot Jupiter.
So here's where we got our data from TESS, our cool telescope. So our data was sourced from the Transiting Exoplanet Survey Satellite, which we kind of got a preview of in our last presentation. And we call it TESS. It's an all-sky telescope and successor of Kepler in helping us learn about exoplanets.
Okay, so we kind of went into what are transits. So here's how we kind of did our transits. So we kind of measured our transits around the test data, right? And we modeled it using BLS. So BLS is the box least squared method, which basically takes these periods, right? You have an area where there's a transit, and then there's a gap between transits. And what the BLS method is saying is, here's the box that has the transit, how much of a gap do we have to put between each of these transits? And that's how you can kind of get periods. So there's kind of 4 parameters that go into making BLS, which is period, duration, depth, and reference time. So reference time is between, period is period between, and then duration is how long does the transit occur, and depth is how deep is that transit. From there, we refined it using a couple of different methods. For example, we use K-transit to kind of like refine it, and in the end, this is what we got for some of our, for one of our light curves.
So, how do we measure transits? They can tell, first of all, they can tell us quite a lot about exoplanets. Depth, which was kind of already mentioned, can tell us how big the exoplanet is. We can find the radius. Period can tell us the distance from the star, of the planet from the star, and the planet's size and mass can give us the density. Using some of the models we were discussing in the previous slide, we learn more about them and we can calculate their characteristics. The most notable one would be the radius, which can be calculated through the formula at the bottom, which is the radius of the planet equals the radius of the star times the square root of the depth on the light curve, which is just how long from the main group to the bottom of the dip.
So here are the exoplanets we measured in this project. Over the course of this project, we measured many different exoplanets, and this list of planets was narrowed down to 6 hot Jupiters. So we have Kelp 2AB, Korat 1b, Kepler 7b, Kepler 14b, Kepler 5b, and NGTS 1b. And over here is just a table of most of our properties for the hot Jupiters
that we used in our project. So going left to right, we have our orbital period, which is basically how long it takes for one revolution around its host star. The planet radius, which is kind of self-explanatory. We use it to measure like volume and stuff. The planet mass, and the planet density, which is how compact are these planets. And we also have the references for where we got the mass from.
Okay, so we kind of talked about density on the last slide. Density is just mass divided by volume. It's just kind of a measure of how compact a substance is. So to calculate the density, which is rho, so on the leftmost side you can see rho p. So rho p is basically just the planet's density. We take the mass of the planet divided by the volume of the planet, and we got that through 3 masses over 4 pi r cubed of the planet. So r being the radius, we just took the cube of r and we multiplied that by 4 pi. So yeah, that's how you get the density of the planet.
So, the big thing with this about why some get so big is planetary inflation, which is basically, with the ideal gas law, assuming pressure and number of molecules remains constant, as the heat rises, the gas will expand, which leads to planetary inflation of these gas giants. This will cause the density to lower because the mass to volume ratio changes.
So how did we measure this planetary inflation? So first off, to measure inflation, you need 2 things. First off, the radius to see how far the planet has expanded because you calculate the volume from the radius. And then the temperature to see how much the gas is being heated. So the radius was collected using our aforementioned transit model, while temperature was collected using orbital period and stellar luminosity. So as you can see from our graphic here of hot Jupiter plus more hot equals hotter Jupiter, which expands it. And then our equation for calculating the planetary inflation.
Okay, so what can we draw from this? So the dashed line, just to kind of start with our graph, is an average Jupiter. So that's just basically, it's taking the radius of Jupiter and it's just saying, hey, this is what we'd expect for all kind of Jupiter-sized planets, right? So here is kind of a version of the graph that we showed a little bit ago, but it includes our hot Jupiters, and as you can see, they kind of fit directly to the graph in the hot Jupiter section. You can see that there's kind of 2 groups of planets here. The kind of lower group on the graph is terrestrial planets, so planets that are more like Earth. So, for example, like Venus, Mars, Mercury, Earth-type planets are all going to be down there. In the middle here, you can see kind of those super-Earths, sub-Neptune planets, which are kind of in the middle. They're not quite gas giants yet, but they're not tiny either. And then up on the right side, you can see all the hot Jupiters. So these are planets that are getting a lot of light and they're being kind of excited by a lot of energy. So they're kind of growing. Their radius is growing far above what you kind of project for planets of their size. So here you can see where Jupiter would kind of show up on this. So it's way off to the left because a lot of these planets are a lot closer to their star than Jupiter is. Because it's really hard for us to detect planets that are further out, as we were saying before. So basically, what you're going to be catching mostly through the transit method is stuff that's really close to the star and is more visible. Okay, so kind of moving on to the next part of this, you can see our kind of U-shaped graph here. So let's kind of go over what this is showing. On the bottom side, on the x-axis, you're seeing planet mass. So this is just basically saying how massive is this planet in comparison to Jupiter. This is measured in a logarithmic scale. So 10 to the 0th is 1 Jupiter. So a lot of these planets that we kind of measured are right around 1 Jupiter worth of mass. So you can see that kind of most of these hot Jupiters fall into the kind of cluster near the bottom. These are high mass, low density, right? So they have signs of just kind of being inflated. They have very high mass, but they're not very dense, which means that they're kind of got a massive radius. This graph also curves back up as mass increases again. This is because as kind of these Jupiters get so massive, these gas giants just gain so much mass, they have the ability to kind of create enough gravity to condense these gases back down. So as you can see, one of our hot Jupiters actually fits into that kind of situation because it's massive. It's almost 10 times the mass of Jupiter.
Okay, so after that, what are the next steps that we would do in the project if there was more time? And that would be probably determining the composition of the planet, so what it's made of. Now, we can make an estimate of that based on the density of the planet, and then once we have that, we can make an estimate based on the densities of other materials. And there's a little graph of basically what Jupiter's made of, as you can see, there.
Okay, so continuing on with our next steps for composition, there are a few issues to this. For example, planets aren't exactly homogeneous. They're not made up of the same element all the way through. And the core is denser than the atmosphere, so obviously there's going to be some discrepancy between the core's density and then when you move out the atmosphere. And the atmosphere is also a mix of substances, though you'll likely have hydrogen and helium there. So as you can see on the graph here, if 0 is the core of the planet and 1 is the surface, you can see that at the core, it has a very high relative density, and then as it goes down, towards the surface, it decreases. So yeah, it's not homogeneous. We don't really know, exactly what's in there without making a bunch of assumptions.
Okay, so there is another next step that we'd like to talk to you guys about. So this would be transmission spectroscopy. So you heard a little bit about spectroscopy in the last kind of presentation, where basically you can see the spectrum of different stars and of different light kind of wavelengths, and certain wavelengths can be blocked out. So what we're basically trying to do, or eventually try to do in the future, would be to kind of look at the star and see which wavelengths are being blocked by the planet, because that could tell us a lot about its atmosphere. For example, if certain elements kind of have absorption lines, such as water or carbon, we could see, hey, this planet has carbon dioxide, or it has water in its kind of atmosphere. So that is what transmission spectroscopy is kind of aiming to do. This has always been kind of an idea, and we've even used these same kind of tactics on stars with dust. So basically, if there's dust in the way of a star, we could have kind of seen what was being absorbed by the dust. But because of these new technologies, we're able to do this more readily, more availably with planets and stars. So hopefully that would be kind of the next step for us. Okay, so here's our acknowledgements. First of all, we'd love to say thank you to Nick Saunders for being an awesome mentor. Slanders. JD Armstrong and our HiStar staff for running this great program and supporting all of us. Thank you, Slavey. So we'd also like to say thank you to Tess and Nexi for the exoplanet data, and Lightcurve and K-Transit for being awesome plots. This template was created by using SlidesGo, Flaticon, and FreePic, and the gift credit goes to cooltext.com. That's it.
All right, do we have any questions? Yes.
I was just a little confused on one of the first slides when you guys said you don't have a hot Jupiter in our solar system, and then you're like, but we have Jupiter.
Yeah.
I got confused the difference.
Okay, so when we were talking about not having a hot Jupiter in our solar system, but having a Jupiter, what we basically meant by that is that we have a Jupiter in our solar system, and we have a gas giant, right? But we don't necessarily have a gas giant that's located very close to the sun and is rotating and is orbiting very quickly. So that's kind of what we were referring to in this presentation. We do have a Jupiter, but it's not a hot Jupiter. Yeah. And if you have any questions, I guarantee you other people in here have the same questions, so we'd love to answer it. Shoot.
What makes it a hot Jupiter then?
Okay, so a hot Jupiter is considered a hot Jupiter because it's located close to the star, referring to the heat, because it's being kind of heated up by the sun more, it's closer, it's getting more light, and it's orbiting very quickly. So hot Jupiters are moving very fast around their star because of their kind of relative closeness, and their heat is coming mostly from being close to the star once more. So a hot Jupiter, as we say, hot Jupiters are gas giants located close to their stars. So basically a hot Jupiter is just any gas giant type planet that is located very close to their star, their host star.
How do they measure the masses?
Okay, so we were very grateful. If you go back to our slide with kind of some of the different properties, we got our masses from all of these different sciences. So I'd like to say thank you to them. I mean, we obviously kind of source them, but when it goes into kind of collecting masses, it's something that we didn't really do personally in this project, so I'm not super confident about answering it.
What's the second most successful way to find exoplanets? That might tell you main measurements.
That would be the radial velocity method.
Repeat the question.
The second most successful way of finding exoplanets is the radial velocity method.
And the radial velocity method can help you because it can tell you how much the star is being pulled by the planet. So as exoplanets orbit, everything is kind of going around the center of mass, which the star is also part of that, right? And obviously the star has so much more mass than the planet that it's pulling the planet way more. But everything is getting pulled in this kind of, I guess you would say, like, system, right? So as the planet orbits, it's also pulling the star. So given that kind of information, you can kind of identify exactly how much this planet is pulling, how much mass it has. This is also how we kind of identify binary star systems as opposed to just regular planets, like hot Jupiters and stuff, because stars obviously pull on their other star way more than a hot Jupiter would pull on its star. So this is generally how we confirm that a hot Jupiter is there instead of a star. Transits are more of a way of identifying that there's something there with the star. Yeah.
Any more questions? All right, well, oh yeah, one more, yes.
So for the transition spectroscopy method, how do you use on that? It's like you're looking at the star spectra of when the planet is in front of the star from our perspective, and from that like spectra you can see the materials that are composed the planet.
So when gases get excited, they can either like absorb some of that energy, right? So in this case, it's absorbing the energy and it's kind of removing these specific wavelengths. So as you can see, certain materials have different kind of wavelengths that they remove, right? So for example, H2O is removing some of these kinds of wavelengths. I mean, it's still relative. Well, we've used this on kind of dust before, so as light comes into the dust, it strikes it, right? Some of the wavelengths are removed because it's kind of exciting this dust, and the dust is like kind of just taking in that energy. So the same thing can happen with a planet's atmosphere. This atmosphere is made of a lot of the same stuff, and as light kind of strikes it, it absorbs some of that energy, and that comes out in some of these wavelengths.
Any other questions? All right, let's thank our speakers, and we'll invite our next group. Last but not least, our Galaxies group. So we have two returning students here, Eskin Jaran, got it, okay. Eskin Jaran, and how many years has it taken me to learn that? We'll find out when I learn it, right? Okay, so Eskin, you're sort of a N-1, I think is where we're at on our Annika scale. Annika being the standard N, and Eskin is an N-1. And Wilson Chow is an N student as well. Is that right? Okay. They will be talking about Galaxies, cosmic makeover, Galaxies redshifting, their style through time.
Alright, hello everyone. Thank you for coming out tonight, or this evening. I'm Wilson Chow.
And I'm Eskin Giraffe.
And we also have another partner, Mackenzie. She was supposed to be here. She worked a lot with our project as well, but she didn't feel very well today, so we'll be taking over her place for today. And our project is a cosmic makeover, galaxies, redshifting their style through time.
So just for a quick background on galaxies, there are typically 3 specific types that we can classify through a process called morphology, which is basically just a study of the different shapes of galaxies. And these 3 types are a spiral galaxy, an elliptical galaxy, and an irregular galaxy, which you can see in the images up here. A spiral galaxy is typically a more younger galaxy and has a more blue color. It's burning a lot brighter, a lot hotter, and it's typically a lot more star forming. That means its star formation rates are a lot higher. An elliptical galaxy is typically a lot older, a little more redder, as you can see in the images here. And it's typically not star forming anymore. It's kind of just sitting in space. And the irregular galaxy is kind of a cool phenomenon. It's the result of different galactic interactions, so like the merging of 2 different galaxies and just different galaxies and their gravitational fields interacting with each other.
So going into more about galaxies and their basics, something we want to highly emphasize is their color. And so what's so great about knowing the color of our galaxies is you can determine the composition of your galaxies by knowing its color. So especially the stars that make up the galaxies, planets, and potentially the black hole. So something you should know is that hot and bluer stars are typically a lot younger, while compared to redder stars, which are a lot more cooler and older. And this is going to be very important later on in our presentation. So looking at our graph, you can see that these are just like a spectral diagram that kind of tells you like how hot the temperature would indicate the color of a star. And also another thing you should know is that red stars are formed more frequently, while blue stars are a lot more brighter, but they do form less frequently.
So in relation to stars, one last just brief overview on the basics of galaxies is star formation. So stars are pretty much what determines, as Wilson said, the color of galaxies. And star formation is typically how a galaxy would grow if it didn't undergo like another more irregular thing like merging with another galaxy. So this chart up here is actually a chart depicting the star formation rates and tendencies of galaxies. So for the x-axis, you have the number of existing stars, which is basically just the stellar mass of the galaxy. And on the y-axis is the number of stars forming, or the star formation rates of that galaxy. And galaxies typically start out their lifetimes pretty hot, like having rates of pretty high star formation in this main sequence, as you can see here. And after they go through their time in the main sequence, they typically either burst into that starburst section and then drop down into the green valley, or just go straight into the green valley in like towards the middle part of their lives. So they're not really star forming at such high rates as the main sequence, but they're not so much as, or they're not like stopped star forming like the red and dead galaxies that you can see at the bottom of this chart.
So in our project, this is what we're mainly focusing on, is redshift. And so something you should know about redshift is it determines how the distance of an object that you're measuring compared to a blue shift, which is how close or how short an object is approaching us. So noticing this, if you look on the spectrum, you can see that a regular spectrum or color spectrum has these emission lines that covers it. And basically what an emission lines is, it's when light is hits a gas within an atmosphere, it is then scattered, and so this is what creates these emissions lines. And so whenever you see a galaxy that is continuously going farther out, these emission lines are then spread out into the spectrum, and it is spread out within the red spectrum. And this is where the process of redshift kind of occurs. And if you see that blue shift is basically just showing us how much the wavelength is being compressed, while the red wavelengths for redshift is being elongated.
So, as Wilson was talking about redshift, the higher redshift you'll typically have younger galaxies, so these more spirally galaxies, blue, And then as you go into the lower redshifts, down to like redshift 0, you'll actually have a lot more elliptical shaped galaxies that are typically a lot red and they're not star forming as much. So our research goal for this project was to determine and examine how the average mass, star formation rates, and colors change as a function of redshift. And redshift, like Wilson said, time equals distance. So we're just basically examining the properties of these galaxies over a function of time.
So this starts off with getting some photometric observations or data from the Cosmic Evolution Survey, which is a survey that basically helps with classifying galaxy properties and galaxy classifications. So first we performed photometry and SED fitting. We didn't necessarily perform them, but we kind of just took some data that was given from the cosmos, and we used it within our research. So some background about what a photometry is that it tells us how bright something is at a certain wavelength or in a given band. So in particular, in our project, we use 3 different bands. One is near ultraviolet, infrared, and optical. And optical is just another way to say invisible light. We also grabbed some data from the spectral energy distribution, or SED, which is basically taking a few photometric points and then fitting it onto a model so that it helps with giving us a spectrum using those points.
So diving into a little deeper about the process of SED fitting, like Wilson said, that was the process used by the Cosmos catalog that we use. That's how they actually got their data. So SED fitting, you basically take these separate photometry images, like you can see on the top, and you fit them to a template to actually get a spectra of your galaxies without actually having to use the process of spectroscopy, which is a lot more difficult and expensive. So it's basically just an easier way to obtain our data, and it's the process, like I said, that we used, or the survey we used in this project performed.
So given this, we started off by filtering data using code from Python, and so this helped with sorting out if we're trying to look for galaxies in particular. And so this really helped with speeding up the process, because as you can see, it really reduced our results from 1.7 million all the way to around 360,000. So that's a pretty big reduction. And also, using the survey, we were able to calculate the mass and redshift, which we're going to talk more later on. And also, when we're talking about completeness cut using IRAC or Spitzer, we're basically talking about whenever in the galaxy, whenever galaxies are always expanding, and so whenever you're trying to grab more observations further out, the resolution or the quality of those images are a lot worse. And so we kind of just factored out parts that we believe would not be detrimental to our results. And so that's what we did with using IRAC channel 1 and 2 from Spitzer, which is a telescope that we kind of grabbed our data from.
So when we first wanted to start looking at the effect redshift had, we actually we came up with this distribution of the redshift in our data set. And as you can see in this graph, it is significantly skewed towards the left-hand side of this graph. So this graph is basically just showing that within the lower redshifts, you actually have a significantly higher concentration of galaxies. And because we didn't want this skewed graph, or the skewed redshift, to correspondingly skew our results, we decided that binning, or placing the redshift into bins with smaller bins in the lower redshifts and bigger bins in the higher redshifts, so that we could just get equal sample sizes, would really help to normalize our results and help to allow us to reach the conclusions that we wanted to reach.
So furthering on what Eskin was talking about with binnings, we basically kind of pinpointed down the parts that had a lot of abundance in galaxies. So if you look here on the redshifts from 4 to 10, there wasn't as much, and so we didn't really primarily focus on getting too much data from there. And so we kind of reduced our bins down to around 0 to 2, and this is where you kind of see most of the maximum of the graph. And so this is where we pinned it down to around 0.25 to 0.5 for our bins. And this is where we kind of isolated the parts where we really want to focus on.
So for our results, the first kind of results that we found were the effect of redshift on mass. And each of these lines is corresponding to one of the bins that we made for our redshifts. So like the blue part of the graph would be a redshift greater than 4. The orange part would be a redshift in between 3 and 4. And it's just, it goes down the list, as you can see through that table. But these results actually showed that with your higher redshifts, you're actually getting a correspondingly higher mass, which was actually the opposite of what we expected. When you're looking at these higher redshifts, you're looking at these younger galaxies that are still kind of at like the early stages of their life. They're still star forming, and we actually expected the like older galaxies that have been star forming for a long amount of time to have a significantly more mass than these younger ones. However, this data we found to be a result of our selection bias. When we were choosing our galaxies, the higher redshift galaxies that we were choosing, because they're so far away, were typically the more luminous, the more star forming, the significantly more massive galaxies, the ones that we could see, which really shows like how much of selection bias we have, as it pretty much inverted what we expected. But there are actually a lot more galaxies that are significantly lower massive in these higher redshifts. However, we just can't see them with our technology available.
Yes, so going deeper into what Eskin was talking about, this can help us find the solar formation rate of most of the galaxies that we were observing. And so if you see here, if you remember looking back at the previous graphs with the bins, this is kind of like flipped. And this is due to analyzing something different on the x-axis, which is the star formation or the log of solar masses per year. And so you can see here that the higher the Z or the redshift, the more star formation is prominent and abundant compared to stars that are lower in Z or redshifts.
So for the last part of our results, we were examining the effect of redshift on color. So we did the effect of redshift on color distribution for the optical band minus the near infrared band, which is the graph on the left, and the effect of redshift on color distribution for the near ultraviolet band minus that optical band here on the right. And while it may not be incredibly clear in these graphs, we found that there were trends showing that your lower redshifts actually had a redder color, which we actually expected because these lower redshifts, these older galaxies, would be like sort of at the end of their like star formation days. They won't be as blue and as bright and as like luminous. They'll be more redder color. And this one on the right, this graph, as you can see by the x-axis, it shows that there was actually a significantly higher change we noticed within these two bands than the other two bands. However, they both were just showing these same trends, that lower redshift, you have a redder color, so your older galaxies will typically be a lot more redder.
So here, going deeper into our results, you can see that anything with a redshift higher than 4 earlier, those are a lot more younger and cooler galaxies. And you may be wondering, what is this red dotted line? And this is almost like a reference point that we use to determine the peak or the mark where more stars that are lower and a lot more redder are beginning to form and who are a lot more dead. And so as you can see, as you progressively go lower in redshift, you can see that there is more abundance in more dead and redder stars or galaxies.
So for some future research, there were a couple things that we didn't really get to touch on in this project that we thought would be really cool to look at in the future. The first one was looking deeper into morphology. I addressed that clearly in the first slide of our presentation, but we thought it'd be cool if we could examine the effect of redshift on the morphology or the shapes of galaxies and see if the shapes of galaxies actually changed as a function of redshift. Because like I said earlier, younger galaxies are going to be more spirally shaped, and your older galaxies are going to be more elliptical. So we're going to see kind of how that process unfolds. And we also thought it'd be cool to look at active galactic nuclei, or active galactic nucleuses, which are basically just looking at the supermassive black holes at the center of these galaxies. And to do this, we would actually use these same catalogs, except instead of looking at the galaxies in particular, we would be looking at the X-ray sources instead, which would kind of give us a little bit more information about the supermassive black holes at the centers of each of these galaxies, which we thought would be really cool as well.
So we just want to say thank you for listening. We'd love to hear any questions. We're always welcome to answer them. We want to give some special thanks to J.D. Armstrong, our very compassionate mentor Finn Giddings, and the Institute for Astronomy, the UH Institute for Astronomy, the University of Maui, Hawaii Maui College for lending us this campus and facility to use, Dr. Park and Ms. Kaichi for helping support HiStar all these years, and also Space Force for funding HiStar, and the Maui Economic Development Board.
All right, do we have any questions? Yes.
Is redshift dependent on the galaxy's age?
So is redshift dependent on the galaxy's age?
So redshift is, I wouldn't say in particularly dependent on the galaxy's age. It helps with finding the galaxy's age because it tells us how far a galaxy is. And so a reference that you can kind of use is that redshift is almost like knowing, or like a way I would kind of explain it is that typically in galaxies, stars that are more closer to the inner circle of the galaxy is a lot more younger, and stars that are older, and stars that are a lot wider or like farther away from the galaxy center is a lot older. So I guess you can kind of say they help with determining the age, but I would say it's the exact way.
And just to kind of add on to that, so when you're looking at higher redshift, it's basically just telling you that you're seeing light from a galaxy. So higher redshift means the galaxy is actually a lot further away. So the light you're seeing is thus like a lot older. So you're seeing, even if the galaxy is old, like at the current point in time, the light you're seeing from that galaxy is actually at a point where it was really young. So a like lower redshift will typically be an older galaxy, while a higher redshift will be, you're looking at the light of the galaxy when it was at a younger point in its life. Did that help in your understanding?
So by that, do you mean you're looking back in time? Repeat the question.
JD asked if you're looking back in time, and pretty much that's exactly what you're doing. You're looking at how a galaxy looked, and you're getting observations of it from a significantly billions and billions of years in the past, which is really, really cool.
Other questions? All right, and let's thank our speakers. That concludes the presentation. For those of you who are here, you probably should be very glad you're here because we had problems with the YouTube broadcast. But we will piece that together and get that posted if you want to review this later, and hopefully I'll be able to get that done next week or two. All right, well, thank you very much.